speaker is Simone and Sartori, talking about voids.
Once again. Hello, I'm Simone Sartori, third-year PhD student at CSFK-ELTE in Marseille, and today we speak with you about cosmic void identification with reconstructed tracer dynamics and why it can be really useful. So, every cosmic void's cosmological analysis must start in the same way. We have to identify our voids, obviously. But this is a non-trivial process, mostly because we don't have a unique definition of what a cosmic void is. However, this is not a real issue. We have just to accept the fact that we can define a cosmic voids from different physical principles. From each of these definitions, we have, however, different systematics to deal with, and we have to pick carefully our definition according to the analysis that we want to do. From this lack of a unique definition, we get a huge set of very different methods of void finding that we can group in three different classes. We have density-based and geometry-based methods. What they do is trivially to evaluate the density field in a direct way in order to find the underdensities. These methods are prone to be highly affected by shot noise. This is straightforward to understand. We want to evaluate the density field in a direct way in regions in which it is really poorly sampled because we are in underdensities. Moreover, when we deal with cosmic voids, we have to be really careful about observational systematics and mask, veto mask. This is true for every cosmological analysis, but cosmic voids are extended regions in the sky, and even in a single object, we can have fluctuation of completeness that can be really problematic for us. To overcome both of these issues at once, a third class of methods was theoretized, methods that try to exploit the dynamic of the mass field in order to identify cosmic void with the information of the whole field and not only punctual information, and to define cosmic voids as basins, regions from which we have an outflow of mass with time. The back-in-time void finder that I'm presenting to you today, or BTPF for simplicity, is a method that is based on this third criteria. It uses cosmic tracers to sample the displacement field instead of the density field, and is probably the first method of this kind to be fully working, that is possible to apply even to galaxy surveys. I claim that this is a new generation survey friendly code because we use a random, we can incorporate every observational systematic on it, and it is optimized for the use of even complex veto mask. It consists on three main steps. The first one is the reconstruction of the displacement field. In a matter of theory, you can provide the displacement field that you prefer, but we developed a new optimal transport code back in time. So if you see different sign in the equation from which what you are used to is this. Why back in time optimal transport approach? Because we don't need any cosmological assumption a priori for the displacement calculation. And this can be really useful. Formally, what we want to do is to minimize a cost function that in our case is the total distance between two sets of points, the position at present time of our tracers, and a set of random positions that mimic the position of the tracers, let's say, in the early universe. In practice, what we do is that we discretize and simplify the problem, and we solve it as a set of small assignment problems in which we want to evaluate quartets of pairs, particle, tracer, random. And we end up with a 24 configurations problem in which we save the configuration that minimize the total distance of these quartets. We iterate until we reach a precision threshold that we want. This code is really fast. because it scales almost in linear time. And usually the speed was the problem for optimal transport algorithms. It is obviously limited by shell crossing, but it works fine in void regions. Once we have our displacement field, we calculate the divergence of it. And this is the field on which we go to identify our cosmic void. It is a proxy of the density contrast field under linear theory. We calculate it trivially exploiting the Gaussian theorem on a grid, and it can be filtered to remove the small scales that are source of noise. Once we have our divergence field, we can locate and identify our voids from the local minima. We apply a watershed algorithm, and what we end up with is a set of non-overlapping regions of the space with negative divergence. Negative because we are back in time. So what we have is a back in time inflow of mass. With the regular flow of time, we have regions from which we have outflow of mass. We validated the code with some tests on boxes and in a light cone, DAISY-like. Let's start from the box. We used the Aletheia simulation from the group of Ari and Sanchez. We used both the halo sample and the at redshift 0 and the DarkMap sample of the box. And we validated it against Revolver, that is a well-known and widely used, even by me, void finder, a geometrical method. I present you two of the most important statistics for cosmic void, voices function and void Garcia cross-correlation function. The voices function on the left, purple for PTBF, orange for Revolver, they are really similar. Our voice function is shifted toward smaller radii, but this is expected because Revolver wants to cover all the space with voids, while we limited ourselves at the underdensities. More informative is the plot on the right. In particular, the monopole of the void Garcia correlation function. It represents the density profile of our voids in different radius bins. And as you can see at the top, density profiles of dynamical voids are more smooth and more natural from the one with identified with geometrical methods. And this can be an hint of the fact that we sample in a better way the underlying mass field of our voids. In boxes, we did also stability test. Let's take a sample of cosmic voids in a given tracer field. Let's rescale our voids to a given threshold, and let's avoid any kind of overlap. When we have overlaps, we pick the voice that is the biggest, and we say only it. In this way, we realign ourselves to some of the prescription of the voices function theory, and we end up with a very different voices function from the one that you observed before. However, this voices function has some characteristics. It is stable to subsampling. So if we take the same sample and we vary the sparseness of it, it must be stable. The only thing that can change is that we can find more big voids if the survey volume increases, and we can end up with a better resolution, so more small voids, if our sample will be more dense. So what we did is to change the sparseness of our DarkMap sample and see how the codes react to it. Geometrical voids on the left end up with very different voices function, very different. And this, for me, clearly a sign of the fact that it incorporates a lot of spurious points. While our method end up with a really more stable voices function across the various subsample. In particular, we can push it to the limit on the right, in which we have basically a perfect match, when we use the real velocities and not the reconstructed velocity. But I want to highlight the fact that we are in a really dense DarkMap sample, and we know that optimal transport is not effective when we have this kind of catalogs with a lot of shell crossing. However, it works pretty well. I end my presentation with the light cone application. we used the buzzer MOX, that is a Daisy-like mock of energy, in our case, with 6 million galaxies. I present you the redshift space and reconstructed space results with the same statistic of before. Thanks to Sofia and Slaja, you already know that redshift space voids can be really useful, and in particular the distortions, but that we have a lot of issues related to the identification of redshift space voids. With my method, we can mitigate these issues. If it works, what you should observe is a small impact on the number of voids between a real space and redshift space, and similar voids function between the two spaces. It's impossible to get the same, and we don't want it, but we want to mitigate the systematics. In this plot, you can see that it works. We have 3 different redshift ranges. Lines are real space voiceless function, while the dots are the redshift space. Obviously, from the voiceless function, you cannot see too much, but if you look at the residuals, the first and the second line, the first line are the residuals for the voiceless function of BTF, the second for the Volver. You can clearly see that in our case, we are always inside the 3 sigmas residuals, while for the Volver, we go up to 8 or 9. And so we can claim that this method is effective on mitigating the issues related to redshift space voids, the identification of redshift space voids. Last test, reconstructed space. We want to go from real space, the redshift space, to real space, correcting for the effect of the redshift space distortion due to the peculiar velocities of our tracers. To do that, we had to explore our displacement and the velocities from our reconstructed displacement field, modifying the classic Nusser and Davis formula. Why? Because the displacement field from optimal transport is biased at this scale with a bias that is basically the linear bias. And what we get is this. What we expect are 2 voiceless functions that are exactly the same between real space and reconstructed real space. And this is basically what we get. Some small fluctuation. Also, a number of voids are very similar. And moreover, the quadruple of the void galaxy cross correlation function should be flat in both cases. And this is what we got, except for really small voids at low redshift. I still don't know if this is a fluctuation, but if it's not, probably I can correct it with a different selection on the smoothing of the divergence field, and not on the optimal transport, because we don't apply different than Zeldovich, the Zeldovich reconstruction, any smoothing. In summary, so I presented you a new dynamical method for cosmic void identification. It is ready to be applied to galaxy survey, probably for the first time. We validated it against Revolver on boxes and Lightcon. It can mitigate the impact of RST up to a factor of 2, and is successful on the reconstruction of real space with our optimal transport reconstruction. What we have to do now is really to publish the paper and start to apply it to real data. Thank you.
That's very exciting. Which data sets, real redshift surveys, do you plan to apply this to? And are you able to be convinced to say gamma? Gamma.
Gamma.
Yeah, okay, then which ones are you planning on?
For sure, Daisy and Euclid. Also because in Daisy and Euclid we don't have for now a complete sample. So the sample that we have has a lot of observative systematic on it. Completeness that change a lot inside the sample. And with classic methods, it's really difficult to incorporate in an effective way is a system of X. With this method, we expect it to be very effective on this. And so the third application will be that. Probably to validate it, we will try to make a cosmological analysis on EBOS, because we already know what are the methods, and then Euclidean methods.
Very nice talk, thank you. When you look at the scale space cosmic web identified with something like nexus or something, when you have voids there, you have substructure in the voids family. So in large scale voids, when you have small scale Shalcos regions, you mentioned that Shalcos works just fine with your code works just fine up to Shalcos and voids, whatever. Are there any limitations to the sizes of voids that you can identify to like the small scale chart? How much does this impede the code?
So basically, obviously, more we loop to smaller voids, more the issues related to the fact that optimal transport is conditioned, say, by the fact that is unable to deal effectively with shell crossing arises. However, as I show you here, and it was something that honestly I didn't expect, even with really small voids, in a pure DarkMap ensemble, in which obviously the effect of shell crossing is really evident, we end up with a configuration that is really stable. And so I really think, and I have to be honest with you, I still don't get completely why, but we get something that, at least in these regimes, it works. It works quite well. Obviously, I tried a little to invert the void finder, make it like a cluster finder. And in this case, we have more issues. But for void regimes, even a simple optimal transport like this, so without weights, without smoothing, it works.
I will ask more questions there from that.
Okay.
Thank you.
Thanks again.